Dear students,
yeah, so here I have the idea of having conformal symmetry is simply that if I make the substitution on the top line here, then if G mu goes into substitution from omega times G mu, but omega goes into omega divided by omega x. Of course, this isn't the variance of the theory, because all I've done is I've multiplied g hat with omega squared, and I rewrote everything in terms of the method g mu, where I made that substitution. I made the substitution everywhere, so it's obvious that g mu always comes from that combination. Therefore, this is a completely trivial invariance. And I want to emphasize how trivial it is. You can do that anywhere in physics. And every now and then I've noticed that other people are doing something very similar, in particular in string theory. This is a well-known trick to add a symmetry to the system, which is totally spurious in a way. And then you draw certain conclusions from the symmetry, or at least you rewrite things and you make it look more useful. So I made that substitution, and then I first asked, what does the Einstein-Hilbert action transform into? And I need these equations. So I mu, the Ricci tensor, changes into the Ricci tensor for G hat. It so happens that I mu, that I mu is really R alpha mu, so there's a contraction between an upper index and a lower index, and that means, and whereas this thing depends on the curvature of space-time. So if this would be just a scale transformation, since there's one upper and one lower index, the omega doesn't enter. So that's why I mu goes to I mu hat. But if omega has time, space-time dependence, then it does change, because there are derivatives in the remote tensor. And I just didn't want to do the calculation here on the blackboard, because that requires quite a little bit of writing. And the calculation is in principle straightforward if you are familiar with the rules of general relativity. If not, I can just tell you what the answer is. And the answer is that you get terms which contain the second derivative of this omega mu in these first two terms. This is the dominant, the most important term. And that is just saying that you have to subtract the trace part. So this is a trace part of that multiplied by g hat itself. So that's an extra term in that equation which you need for detailed calculations, but it's important for the main story. And then there's also a term which contains quadratic functions of the derivative, d mu over time, d mu over with again a trace part as the last term. And but then only happens when the derivative of omega really becomes large. Then you get those extra direction terms. The first one, these first two are more important, but omega is very close to identity. Right? If omega stays very close to identity, then this is a quadratic term, this is a linear term. The linear term will start off to dominate the expression. And so you find that the Ricci curvature depends on omega. So if you make a conformal transformation, omega is not a very special function, then everything changes. Now, if you look at the action, something remarkable happens. If I look at square root of g times I, now I is the Ricci scalar, and I didn't mention how that transforms. I should have added I hat no, sorry, this does tell you how the Ricci scalar, if you take trace of the Ricci tensor, I get the Ricci scalar. So if you multiply that with G hat mu with the indices upstairs, well, if you multiply the G mu with the indices upstairs, then I get x factor omega to the minus 2. So now you get, if you make a substitution for taking the trace of this, you have to multiply with, you get omega minus 2, but then if I have the determinant of the metric in front, that's an omega to the power 4. So I get the omega minus 2 times omega to the power 4, so it gives me omega plus 2. So now you get a scale dependence in the Ricci scalar here if you multiply it with the volume of space-time. But you multiply with the volume of space-time if you're interested in action. And then, this is how a scalar transformed. So you see that to keep things a bit short, I skipped a step in the calculation, which makes it perhaps a bit hard to follow. So you first can trace this, and then multiply it with the volume factor. And then this is the way it transforms. In this term here, you have to take a trace, and the trace adds up to actually factor 6, because you get the trace of this, which is 2. The trace of this, if you multiply that with G mu nu with 2 upper indices, you get the trace of G squared, and that's 4. So this contributes 4, this contributes 2, altogether contributes 6. And that is this first term. The last term, if you take the trace, something of a miracle happens, which is that if you take the trace, you multiply with G hat mu nu upstairs. But if you do the same thing here, then you get a factor 4. And you get the same expression as you have here. So this 4 minus that 4 gives you 0. So this term accidentally cancels out in the action. This actually was the reason why I wrote omega squared. Because you could have asked, why square? Why not to the power of 15? Or why not just omega itself? Or why not an exponential, which many people do? Well, I needed this to be omega squared just because I like the idea that this whole term cancels out. It only cancels out if you write omega squared. That gives you a factor 4 here. Otherwise, this quadratic term would not cancel out, and my life would become more difficult. And so now the action just goes into this. And then I'll rewrite it by saying this is a quantity times the second derivative of a quantity. Well, you know from quantum field theory, if you have such a thing in the action, you can do the partial integration, because in the action you have to integrate this over space and time. And when you integrate something, you can do partial integration. So partial integration tells you that all these derivatives can be put to the other side. This is a covariant derivative, capital D. Capital D means that the Christoffel symbols will also be in there, and it makes it a bit more complicated, but it's such that if you have a covariant derivative, and then the effect of the metric tensor itself disappears, because you can take that to be flat, and then the covariant derivative just acts on omega. So, by partial integration, you let the derivative work in the other direction at the cost of a minus sign. So you get now a plus 6 instead of a minus 6, and you get this one derivative acts in this direction, so d alpha omega times the beta omega, and omega squared. Alright, so this is what happens, and now I'm making a little substitution. Just first of all, replace put there a factor I, which, because this has strange plus signs in the action, where normally I would expect a minus sign. In my definition of an action, the kinetic and potential energy both come with a minus sign. So, for all the other fields, whereas here you get a plus sign. If you have a minus sign, you see it's always the minus inverse of that gives you the propagator of a field. So the propagator becomes plus 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 if you have minuses in the direction. So that for later calculations that minus sign is useful. But in this calculation, you get an anomalous looking plus sign where you want the minus sign. So I multiply omega by a factor I. And I put a coefficient kappa, which is not the coefficient kappa people normally use, because this time I want to get rid of this factor 6 here. So kappa normally is the square root of 8 pi g, but I divide the square root by a factor 6. So now it is this term which becomes the canonical term minus 1/2, or let me see, yes, that is, or in the action there is a 16 pi g downstairs. So that gives me an extra factor 1/2 here, but so everything is being really divided by 12, and so you get the minus 1/2 minus 1/12. So this comes from here and this comes from there by the rearrangement of terms. So this is just a rotational question that you should pay too much attention to. But basically then I end up with this action, and what I did, I also added a cosmological term. And that is for later use. I also want to see, eventually I want to have a theory that also handles the cosmological term. And the cosmological term is just basically the square root times g times lambda and then nothing else. The square root of g goes like overlap to the fourth. So that gives me an overlap to the fourth term, so it also gives me an 8 to the fourth term. And it had a minus sign in action, but because of these rearrangements of terms, I end up getting a minus 136 kappa squared. So the tilde, or I should say, the tilde refers to the anomalous 6. So normally people write kappa is square root of 8 pi g. So kappa tilde has that divided by square root of 6. So I end up with this action, and the observation is this first part looks just like the action of a scalar field. In fact, having a term minus 112 phi squared is a thing one often does in conformal invariant theories. You find that without such a term, this theory is nearly but just not quite conformal invariant. If you would have flat space-time, everything would be fine, and the scalar field would automatically be conformal invariant, provided there's no mass term. But if I would not be equal to 0, then you get a correction. So in ordinary conformal theories, this looks like a somewhat strange correction term that people add all the time. But now you see, in this case, it comes from the Einstein-Hilbert action itself, which had originally as this times I divided by 16 pi g. This was the original Einstein-Hilbert action. So now you see that I transformed that, and it becomes this. And now you see that the R term, which was the dominant term in the Einstein-Hilbert action, now becomes a sort of added correction, and a dominant term seems to come from here. That's a subtlety that's quite interesting in this theory. And then I can treat this as a conformally invariant theory. Before going into the details of that conformal invariant theory, I first want to mention something else. The day before yesterday, I said that I had a theory for the S matrix of a black hole, saying that ingoing particles affect the outgoing particles by causing a shift in this direction. And now let me see. I'm trying to remember how far I got last time. It was so. I just realized there was still a topic which I also wanted to mention there, and that is that this shift means that there was an algebra. I did mention. Oh yes, I remember I ended writing down this amplitude last time, and it's going to be related to this. I wanted to write this amplitude as a function integral dx mu, and then have e to the minus I dx squared, and there was a plus x dot p, where you had both x plus p plus and you had x minus p minus. So this was, I could take these two terms, and no, I should say it this way. Plus, minus, plus. Say it this way, that it depends a little bit how you define the indices. If you write them all as upper indices, then there's to go this combination. And this is, of course, the Lorentz invariant inner product of p and x. And that's where I left last time. What I still wanted to add is that this leads to an interesting algebra. Because you can do this in ordinary function integrals for x variables and p variables as well. And you find that this is quantum mechanics, where the x and the p are actually algebraical objects. They are operators in the Hilbert space. Yeah, I have the Hilbert space of in states, the Hilbert space of out states. I could map one to the other. I could map the operators p of x, say, or the in particles, and find that they give a shift to the outgoing particles. So basically, that shift could be written as x of out, or is actually the angle omega, x of out, the omega, so that the in particles caused a shift of the outgoing particles. And the shift was given by an equation saying that if I differentiate twice the vector omega, and then there was a constant, times the shift of the outgoing particles, then that equals the p of the ingoing particles. You can rewrite that. Oh yes, this is the Laplace equation for the ingoing particles. So the opposite also happens. If you have this, you can say also that the d omega squared minus 1 of the in particles also shifted, and that's minus the out of omega. So these are now operators acting on the particles, on the states of Hilbert space, where you have a choice. When there's a piece of the horizon, you can either describe the ingoing particles in terms of an operator p in of omega, which gives you the momentum distribution over the horizon of all the particles at the moment in. And you can, at the same time, you can consider the position of these ingoing particles, and you write it as xn of omega. And since all these particles have their wave functions, these operators just obey mutual commutation rules such that x in omega, p in omega, that these operators are just I delta omega minus prime. So if I look at different positions, the particles, the positions of the particle are irrelevant. But if we look at one single particle going in at one single value of the angle, then that one single particle has a wave function. But if I compute the momentum variable of the wave function or the position of the wave function in the same direction, then of course you get the familiar commutation rules between position and momentum. So what I end up now is a new algebra for the ingoing states where the momenta of the ingoing particle and the positions of the ingoing particles are algebraic operators that obey commutation rules. And what the consideration of last time can also be seen to lead to is that the entire Hilbert space of all the ingoing particles can be mapped onto the Hilbert space of all the outgoing particles, provided you identify the in operators and the out operators this way. So momentum and position interchange momentum and coordinate interchange their roles if you look at ingoing and outgoing particles. I found it extremely interesting to see how that comes about. And one of the interesting things is that momentum distribution and position is the only variables that goes into this algebra. All the other properties of the particles are immaterial. So you can also say, wait a minute, but I thought there were different species of particles. What species of particles goes in, it doesn't matter. The shift in the outgoing particles are only dependent on the momentum of the ingoing particles, but on nothing else. So the nature of the particles doesn't enter the algebra. So if this is a baryon or a lambda, that piece of information disappears. So the baryon number cannot be conserved in this theory. The outgoing particles do not care about the baryon number of ingoing particles, so baryon number becomes a meaningless concept. Baryon number cannot be conserved. And the same for all the other quantities, with the possible exception of electric charge. Because when particles are electrically charged, if the ingoing particle is electrically charged, you can compute what happens when two electrically charged particles cross each other. Well, if they move very fast, they have electric and magnetic effects on each other. So having a very fast electrically charged particle moving in does have an effect on the electrically charged particles going out. So what I did here with momentum and position, I can also do with electric charge. Yes, and what? Well, it turns out that the electric charge distribution, rho omega, has the same relationship to the phases phi of omega of the wave functions as all the momentum has with the position. So you're just rotating in on a circle in phases. Right? So if you ask how the state of the wave function depends on the phase, then you get the amount of electric charge. So and that leads to the charge density. So charge density and the phase of the wave function has the same relation as momentum and position. So you can generalize this algebra to also include electric charge. Once you have electric charge, you can continue. Say, wait a minute, what about non-abelian charges? You can do the same thing again. So you can extend this algebra to include at least some of the interactions of the standard model. But then it gets hard. You need to think of the Yukawa forces. How do I add that in? Well, that is quite a complicated material, and I haven't been able to sort it out completely. So it's still somewhat mysterious how to do all that. It's also questionable whether we are on the right track, because this algebra still is infinite. And what I said last time is I don't get a finite dimensional theory of microstates. The microstates are defined by these functions x of omega and phi of omega, which are continuous functions, and the number of degrees of freedom of this function is strictly infinite. So I get an infinite set of microstates instead of finite ones. This must have to do with the fact that particles shouldn't come too close to each other, then they will make black holes. So there's a cutoff in the theory, but you don't know yet how to implement the cutoff. So all that was part of the story which I wanted to mention last time. But you see, what really went in is that you can either describe the Hilbert space in terms of ingoing particles or in terms of outgoing particles. And now I want to go back to this story and say this is related to that. Why is that? Well, you see, you have this complete conformal invariance. So what I can now do is choose the conformal gauge. You see, we have a local gauge theory, and I really hate about that. Of course, you can fix the gauge and fix the coordinates, and that's something we indeed will have to do. But you also have to fix this omega, or rather, actually, you have to fix what you do here. Which of this capital omega do we choose? We are free to choose anything we like. Well, what you see, and this is why I wrote this equation on the blackboard at first, you see that if you choose your little omega differently, then the Ricci tensor becomes something different. And Einstein's equation was that capital G mu nu was 8 pi G T mu nu, where G mu nu just happens to be the combination I mu nu minus 1/2 I G mu nu. So this is just, again, the Einstein's equations contain double indices, so you can also have these problems with these traces you have to remove. This is not so important. But you find that G mu nu will not be variant under these transformations. If I now ask how does G mu nu transform, it again contains this term. This term now cancels out. Look carefully, then removing that one minus 1/2 trace removes this term. So G mu nu basically goes into G mu nu, and now I forgot whether it's plus or minus 3, it's plus, no, minus 2 omega minus 1 d mu omega. Yeah, there could be order d omega squared, but I'm not going to look at that. I'm going to make an infinitesimal conformal transformation, and then on the linear term Naples, and not this one. So this means that if I consider a general transformation, unless I enforce this thing to cancel out, which sometimes you can do, that you don't need omega itself to be 0, but if you manage to get this property moment 0, then the conformal symmetry remains. And that happens if you are in a flat space-time and make the inversion, x going to 1 of x. Then space-time remains flat, because if it was 0 in the beginning, it remains 0. But in general, it depends on my choice of omega. This omega depends on capital omega. So now comes the trick of fixing the gauge. This G mu first then is T mu. So, because of Einstein's equation, T mu then also gets modified this term. That means that if you make a generic conformal transformation, you modify the energy content or the particle content of the system. So this is a symmetry that doesn't leave the number of particles in the world invariant, like normal symmetries. They refer to particles, but they don't add or remove particles to the system in general. But here it does. So here the conformal transformation modifies the thing which I call T mu nu. At least it does so if I would identify G hat as magnetic. And normally I would not do that. I would identify G mu as magnetic, and then nothing happens in this transformation. So, if I promote the ether field to be a dynamical looking object, then the T mu changes. In fact, you can actually see that there's a strong relation between this G mu and the contribution of T mu from the ether field. So anyway, in general, I have different amounts of particles, but now I have the choice of choosing different gauge fixing procedures for the invariant particles. And the problem, however, is that I have only one function omega x that I should fix with the gauge choice, but I have 10 components of T mu nu. Well, in the conformal theory, it's actually not 10, but 9. And that is that the trace T mu nu will always remain 0, and that's because in conformal symmetry, the trace is precisely telling you what happens on the conformal transformation. If your theory is conformally invariant, the trace of the element tensor vanishes. So, for instance, the maximum field, if you compute the trace of the elementary contents, it's not such as a pointing that the trace vanishes. So, what I can do now is okay, I can only look at one component of T mu nu and force that component to